Good evening, everyone, once again. Last week, we looked at the fundamentals of neural networks. We looked at the basics. We looked at the neuron. We looked at perceptrons. We looked at forward propagation and back propagation. And then we also looked at things like optimizers, which are new, ideas that really apply when you come to neural networks and then deep learning. And then we also looked at the concept of a layer, and we implemented a basic neural network, a basic neuron rather, using our hand coded, just writing it by hand. But writing by hand is not the optimal way of building neural networks, especially the complex ones that we have that we use today, these days, right? We have high quality, high, level frameworks that are, quite advanced in a lot of different ways that are available to us, right? Um, Over the years, they have evolved and they used to be a lot more in the beginning, but I think over the years, um, they have basically evolved. Initially, we had some proprietary ones. I had to pay money, or it was, the code base was closed and, unavailable and so on. And then we had the one that Google really came onto the scene. We had the likes of Cafe, Tiano, and so many other ones. Then we had a Torch, which was running on C plus plus. And then Google came up with TensorFlow, which runs on Python. And then after that, we now have we had PyTorch. So PyTorch was basically Torch, but was implemented in the Python programming language. And those two, TensorFlow and PyTorch, kind of started growing, and they gained a lot of following, mainly because of their capability to, handle really large workloads and simplify things immensely. The whole idea, the ideas of, practical application and implementation of neural networks, you know, are complex beyond the maths, beyond the theory, which we looked at last week. There's also the aspects, the engineering aspects of it, like scaling up, performance tuning, um, you know, bottlenecks in the whole pipeline, data loading, data cleaning, training the networks, checkpointing, keeping track of the training. Remember the weights that you are training, that's the knowledge. The knowledge is in the weights. So if you lose the weights, you've lost the knowledge. You've lost all that you've done. So imagine like if you had been training a model for 1 week and then something happens and your drive crashes and you lose the weights. You lost all of the work of that 1 week. So you have to start from scratch. And of course, if something happens, and there's a crash, even if you were storing the weights, are you able to keep track of the work? It's even possible that you could store weights somewhere on a disk or even back them up on an S3. These are now engineering, this is the engineering uh, layer of thinking, right? You back it on S3, but what of the one that is currently running? And something happens, the server crashes or something, you can still lose hours of work. So all of these things, all these complexities, all these headaches were handled or have been handled well by all of these frameworks. So it became very easy for people to adopt them and use them, because then you don't need to be thinking about if I'm training my model, how do I keep track or how do I keep backups of the weight as the model is learning and learning and learning? You know, um, what happens if my server crashes? How do I recover and all of that? So PyTorch really was really adopted um, shortly after it came on. Initially, people were always comparing with TensorFlow, and it couldn't do as much as TensorFlow, but the main thing with PyTorch is that it's open source. right? So a lot of people contributed to it and it has grown. The second thing we'll look at it is PyTorch is really easy to use. It's really easy to think about how to use it when you compare to things like TensorFlow. They both use what we call a graph, a graph approach to building what they call a computational graph, right? And those are some of the methods that you have to use for you to optimize performance, speed of training, speed of inference. So anyway, PyTorch has taken off. I think PyTorch is right now the most widely used training framework for neural networks in the world. Maybe it has overtaken TensorFlow. There was a time TensorFlow was number one. But it looks like TensorFlow is generally getting phased out. So PyTorch has kind of taken over. Google is replacing TensorFlow with JAX. So people are also looking into JAX, and there are a bunch of other ones in other programming languages. There's a programming language called Julia, which also may have its own training framework. But so far, when it comes to training neural network models, no other programming language beats the Python programming language. So we are going to look at PyTorch. Um, we'll see how we can use it and how we get the best of it. PyTorch is an open source machine learning and deep learning framework. It facilitates building and training of your AI models, no matter what kind of AI models. And it uses a Python API. So what that means basically is the way you write codes is not different from Python. It still looks Pythonic. There's this terminology when we say something is Pythonic. Basically means that the way you write the code, you follow Python's, you know, conventions and, the things that Python developers love. You can use functions, you can use um, 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 the different Python data types, the tuples, the lists, dictionaries, and then you also have things like list comprehension and all of those lambdas and so on, all of those aspects of the Python programming language that make Python Python. So PyTorch is known for its flexibility for ease of use and the dynamic computation graph. So unlike a TensorFlow that has a static computation graph, which if you're using TensorFlow, you have to build your computation graph and then you run it. And this is typically what happens in all cases. But for PyTorch, yes, you still build your computation graph, but you don't focus on the computation graph. You rather focus on building your models. You think of layers. That's what you think about, which is easier for most people to think about than thinking about a computational graph, which I'm not going to go into computational graph right now because it's a pretty complex subject and can be a bit abstract. But it's good to know if you want to if you want to delve rather deeper into how all of these frameworks actually speed up training and inference. All right. So because it uses dynamic computation graph, it's very popular. We use it both for research and production because it means you can easily tweak stuff and you don't have to recompile and all of that, right? And everywhere, computer vision, NLP, anything, right? So basically, this is repeating the same thing. The graph is built on the fly during execution, right? So think of it like um, some programming languages where you have to write the code, then compile the code, right? Then run the code. So a good example is C++, um, and all the others, right? But you have a programming language that like Python, which is not a compiled programming language, it's an interpreted language. Or another programming language like PHP, which is also an interpreted language. You don't have to compile it, you just write the code. JavaScript is another good example. JavaScript is more of a translated um, programming language. So you just write the code and you run it. There's no compilation step, right? So in the same way, with TensorFlow, you have a static graph. You have to build your computation graph, you know, and then compile it. And in fact, building a neural network with TensorFlow was very abstract until they introduced Keras. Keras is now another layer on top of TensorFlow that kind of abstracts away and hides that computational graph aspect of it. right? So in the same way, PyTorch, they have this, um, you know, um, dynamic graph. It's built on the fly during execution, so you don't need to do a static compile. There is program control, which you typically cannot do in a computational graph. But it well, you can't do it naturally the same way. Um, but with PyTorch, it makes it easy. It's ideal for research, for building custom models, for debugging complex logic. So, like I said, the contrast is that with TensorFlow is a static graph, while PyTorch is it's a dynamic graph. So as you define, it runs. So Python is the Python code that you are writing is the model for the graph, right? That's what makes PyTorch different. PyTorch is also research friendly. It's Pythonic, like I said. Basically, everything looks like Python. You don't feel dislocated or confused, when you are using PyTorch. It's an intuitive API. It uses object-oriented approach of Python. So everything is a class. Your objects are encapsulated in classes. So like we did last week, where a neuron before when we were training, we used to have things flying all over the place. We have the parameters, in one separate variable somewhere. We'll have the gradient functions and all of that in different places, right? But last week, for the first time, I brought everything and put them under a class called neuron. And you had the forward class and the backward class, and then we had the parameters as properties of that class. And this is basically the principle because it helps you to just encapsulate everything in one place, and you don't need to be looking for where are my parameters and so on. So and that's how PyTorch implements the same thing. And it's easy for debugging. You can just use print statements to get the current value of things, or PDB. It's popular for academic research, rapid prototyping, and new model architectures. And it also has a strong industrial adoption. It's used by Meta Facebook. Facebook is actually the company that first of all pushed out the first versions of PyTorch, right, and open sourced it, and then of course everyone followed. Then Tesla, OpenAI, Microsoft is also a backbone for a bunch of other tools, including the Hugging Face transformers, which we have seen. PyTorch Lightning. So PyTorch Lightning is a library built on top of PyTorch that basically automates the training cycle. We're not going to go into PyTorch Lightning yet. We'll first of all use PyTorch just to build um, our own training loops. But after we have built the training loops, then we will be able to understand how PyTorch Lightning helps by abstracting away all of those, um, training loop stuff. So we'll look at that later on. Then Stable Diffusion, of course, Stable Diffusion is also a company that basically focuses on building um, vision models, right? Or image models. So models that can generate images basically from prompts. So with PyTorch, it's also very easy for you to seamlessly transition from research into production. So after you've done your research, it's very easy for you to then upgrade it because for research, there are a lot of things you don't bother doing. You're just testing things. So you don't think about scaling and all of that kind of stuff. But once you are done, you now want to add additional buffers to your code, right? So PyTorch makes it easier for you to do that. So let's go into it. First of all, PyTorch, you can easily get it here. So their site is PyTorch. So it's pytorch.org. So you just go to pytorch.org. And one thing you will find with PyTorch, they have a very huge community, very helpful community. There's a whole lot of different you know areas if you need to ask questions or find out more. The other thing with PyTorch is they have really excellent documentation. You just go to docs, PyTorch, and we're going to use some of the documentation today just to try out a bunch of things, right? But they have really, really great documentation. You can actually master PyTorch just by going through their documentation. You can see their documentation has a lot in it. So we'll touch some of these things. We cannot actually cover everything. There's a lot here. We'll touch some of them. So that's just to tell you. So some of the basic concepts that we are going to look at, PyTorch is built around a bunch of basic concepts, which if you go to the user guide, you will see, you know, you see it talks about a lot of basic stuff. So you're going to talk about tensors, right? We'll define what is a tensor, data sets, data loading. So we use scikit-learn for data loading. But when you're using PyTorch, you're going to have an end-to-end pipeline as well. So PyTorch also allows you to handle data loading and you build it into your pipeline. So it makes things easier. Transform is when you need to change data. So think of transform as feature engineering. It's a transform that help you to transform data in one shape to another, which is essentially enables feature engineering. Then you now build a model. And then you have autograd, which is automatic differentiation. Then you have the optimization loop, which is a training loop itself. And you look at other things like how you can save and load and then use the model. So let's look at a bit of the theory before we go to it. So first of all, what's a tensor? We're going to look at it. A tensor is a fundamental data structure in PyTorch, and not just in PyTorch, in machine learning generally. Prior to now, right, we've been doing maths, we've been dealing with data structures that basically are what we call scalars, single numbers, or vectors, a list of numbers, or even matrices, which is a two-dimensional structure that contains numbers in rows and columns. That's probably the highest that most people have handled data. Like a spreadsheet. A spreadsheet is a matrix, basically. It's a two-dimensional array, right? Or two-dimensional sheets. Let me use that word of numbers, right? And that's a matrix. But when you start talking about three dimensions, cubes, fourth dimensions, and fifth and sixth are multiple dimensions, right? It begins to get more difficult for us to visualize them. So we have what we call a tensor. A tensor is a general name for any multidimensional array, starting from a scalar, which is a zero-dimensional array, to an n-dimensional array. And we'll talk about that. For those who have looked at NumPy, you see that's what a NumPy is. NumPy is basically an ND array. NumPy is an n-dimensional array, right? But unlike a NumPy array, which we may have been familiar with, NumPy array doesn't bother about where your data is stored or where the computation is done. Now, the PyTorch tensor is now device aware, and the tensor is the basic unit that you can use to determine where computation happens. So a tensor knows where you put it. In other words, you can decide that this tensor should be in the CPU. In other words, any computation that is done with that tensor will be done on the CPU. Or you can decide that you want to put a tensor in a GPU, right? And if you do that, any computation you do on that tensor will be done on the GPU. And of course, we know that GPU is what makes computation so much faster, that machine learning with neural networks has become not just realistic and practical, but has basically upended every other thing. So we'll talk more about tensors. Then we'll talk about autograd, which is automatic differentiation. PyTorch has a module called autograd, which automatically calculates gradients of all operations that you do on tensors. And you may ask, how does it do this? Well, you can look under the hood. Remember, we did a bit of gradient calculation when we're doing loss functions and how to calculate the gradient of loss functions. And even the task that we have is calculating gradient of the activation function. So every bit of operation that you do, as far as neural networks and machine learning is concerned, you have to do the gradient. You have to be able to calculate the gradient of that thing, because when you are doing back propagation, we will use the gradient for the backward pass, which is basically to say, okay, to calculate how much of the error from the um from the output, should be uh propagated backwards, and then how much of that error should affect which parameters. So the gradient is a key element, and is crucial for back propagation. Without back propagation, you cannot train neural networks, because back propagation is a process, like I said, of determining how much you should adjust each parameter based on the gradient and the power of the signal, right? So the good news is that Torch does that for you automatically, so you don't need to think about it anymore, right? Then, like we mentioned earlier, PyTorch has a dynamic computational graph, right? So you just define and it runs, on the fly. The computational graph is built on the fly as the code is executed. So you don't need to pre-compile it or anything. The beauty of this is that it helps with the workflow. You just make changes, you run, make changes, you run. You don't need to, you skip an extra compile step where you would have been change, compile, run, because sometimes that is a problem in the sense that you may actually forget to compile, and then you say, oh, this change I made didn't work, oh, not realizing that you actually forgot to compile it. So it simplifies debugging and allows for a flexible model architecture that can change during runtime. Yes, because static graphs, you cannot change the architecture during runtime. In other words, you cannot, while you are doing inference, you cannot attach some additional layers and things like that. Then PyTorch has this torch.nn module, which is the main module that, the package rather, that provides all of the building blocks for building neural networks, including a wide array of layers. So we're going to talk about layers. Remember last week we talked about the fact that a layer is essentially a bunch of neurons that operate in parallel. So the data that comes into the layer, each neuron directly receives an input, does its own, has its own effect, right? Or in this case, does its own calculation and then sends an output to the next layer. And the connection from the neurons in each layer to the neurons in the next layer is what determines whether, it's a fully connected network or a fully connected layer or what. We're going to look at that shortly. So there's a wide array of layers which are now easily implemented. So you don't even need to do the maths yourself or do the implementation yourself. You just bring them in and use them. Activation functions as well, which we looked at, and then loss functions, right, which you can use to calculate loss. And so typically you build a model by subclassing the NN module and then doing stuff in the child class. Then we also will talk about, I mentioned data sets and data loaders. So PyTorch also offers these utility classes, the dataset class and data loader class within the torch.utils or data submodule. And that helps to streamline the process of loading data, batching data efficiently, right? Because when you are training models with large data sets or even large models, you find that you cannot load all the data at once. What we have been doing all this while is we will load all the data at once, okay? And for data that is only 10 rows or 100 rows or even 1,000 rows, that's okay. You will not crash. You will not run out of memory and crash, by running all your data or training with all the data at once. But now think of a situation where you have millions of data. You cannot load all of those millions of data all at once. You don't have enough RAM, to do that. So it will crash. So what do? We do what we call batching. Batching is a process where you take the data, you split them into batches. So if you had 1 million or 1 billion data rows of data, you say, okay, I need to train on maybe 1,000 at a time or 100,000 at a time, right? So you load that. So all of that is handled by the data loader, instead of you having to run all of that batching by yourself. Then, of course, we talked about GPU acceleration, which because you have the tensor, um, PyTorch has built-in support for CUDA. CUDA is a library that you use um, for doing computations in NVIDIA GPUs, right? So if you don't have CUDA, you cannot do anything on NVIDIA GPUs, basically. So, and others have their own libraries as well, but I think NVIDIA is the one that is most popular, and most people, we have to learn how to do that. So Python has built-in support for CUDA. So the interesting thing is that CUDA is a separate programming language of its own, which you would have to write by yourself if you were trying to, write training, code to train your models. You would have had to learn and write CUDA, learn and write, or learn to write, how to do computations, how to program your computations in CUDA. But PyTorch takes all of that stress away from you, the user, because it does all of that implementation. So you don't even need to. The same code that you wrote to train your model in a CPU, you'll still use the same code to train your model in a GPU. But it's not actually exactly the same code. What will happen is the code will be compiled into CUDA commands, right? Which are basically, CUDA is basically um, based on C language. So you're going to compile it into CUDA, which is based on C language. And those commands will be loaded into or moved into the GPU to run. So this is why PyTorch is so popular, because it takes a lot of stress away from us. So this is just this table just shows kind of, if you now want to link the concepts to the code. So a neuron is represented with a linear layer, an end of linear, which is a layer. This is like the simplest layer, and we're going to look at a linear layer first. Basically, most layers can be represented by a linear layer, and then you add an activation. Okay. The activation function, which is what I just mentioned. So you can have any number of activation functions, right? So you just stack layers, and that will form your networks. Then we have the forward propagation. You just call the model and pass your inputs, the X values, right? And you forward propagate everything all the way. And then loss function, this is an example. There are many other ones. Then the backward propagation, you just do loss of backward, and it's basically going to take the loss that comes out at the end of your network and back propagate it. And in back propagating it, it calculates all the losses backwards. And then you now use the gradient descent, the optimizer dot step, which runs through each layer backwards and updates the parameters. So we'll look at each of these in detail. First of all, we'll start by first building up, a network and understanding how the code corresponds to the architecture. And then we'll now do a training loop. So I already talked about tensors to a certain extent. A tensor is a multidimensional array, right? It's a generic representation, and it is a core data structure in PyTorch. Everything is stored in a tensor. You really cannot do anything in PyTorch without, first of all, converting it to a tensor and storing it as a tensor. You cannot do any computation if you do not create a tensor first, right? In normal Python code that you write, you can just say x equals to 10. But if you want to do that with PyTorch, you cannot just do x equals to 10. You will have to create a tensor first using 10, right, as a value. And then when you create a tensor, then you can then use it to do your computation. And the tensor, like I said, is a multidimensional array. So it's a generalization of a scalar. Like I said, scalar is a um, zero-dimensional tensor, basically. It's a tensor that doesn't have, it doesn't have a width or a height, right? It doesn't have a length. It has a single value. That single value is whatever value assigned to it. So that's why it's zero-dimensional. A vector has a length, right? Basically, think of it as a list, okay? And if you look over here, you see some of the visualization. So a scalar is a single value, 1 or 11, while a vector is this. Think of it in this way. This is how we represent it mathematically. is one dimensional, right? This is dimension. It only has a length. It doesn't have a width. Even though you could say it has a width of 1, but a vector is essentially a matrix that has a width of 1. So we normally ignore that width. We just say it has a length. And in this case, this vector has a length of 2. It has two numbers in it. This other vector, which is a row vector, you could have a column vector, and you could also have a row vector. So the row vector has a length of 3, while the column vector has a height of 3. But in both cases, you can generally say the same thing about them, that they have a length or a size or a dimension of 3. Okay, so this is a row vector and this is a column vector. This is a mathematical representation of a column vector, while this little thing in here is actually a mathematical representation of a row vector if you were to use mathematical symbols. Okay, so that's a vector. A matrix is a two-dimensional array. This is a matrix and this is a matrix. It has rows and columns, right? So it's two-dimensional array. It's a two-dimensional data structure. So you can see it has rows and columns. Then a tensor, basically all of the previous ones I mentioned are all tensors, right? But in most cases, when people say tensor, they mean from 3 dimensions and up, like this one, because you really don't have any other name for a 3-dimensional array, right? So we just call them tensors. But strictly speaking, a tensor, all of these, they are all tensors, right? So either way, you can understand the context depending on how it is used. So in this case, you can see it has 3 dimensions. It's difficult to kind of represent this on a flat surface because the maximum you can do intuitively for human eye to understand on a flat 2D surface is a matrix like this. But once you go to 3 dimensions, it's easier for you to represent it like a cuboid or a cube in this way. So you have the length, you have the height, and you have the depth. Length, height, depth. So that's typically a tensor. So this is for a 3-dimensional tensor. Now, how about a 4-dimensional tensor? You can see how difficult it gets. How would you represent a 4-dimensional tensor? Maybe the 4th dimension will be multiple tensors. So you can see that human beings are limited because we can only perceive 3-dimensional spaces. After the 3rd dimension, a 4th-dimension space is difficult to perceive. So we look for other ways to do that. And that's why when we talk about PCA and dimensionality reduction, you see that we typically take a multidimensional data structure and we reduce it to 3 dimensions so that we can visualize it, right? But in this case, it's 3-dimensional, but for us to visualize it, on a 2-dimensional space, you see that we have 1, 2, 3, 4, but this 4 is really difficult to think about it, right? It's actually four, a stack. Think of it as a stack of 4 matrices, right? Or a stack of 2 matrices, you know. So, like I said earlier, the uh tensor is similar to NumPy tensor, and there are 2 key things that you need to remember. Okay, let me mention the 3. The shape, it always has a shape. A shape is a number that represents, the dimensions, in a tensor. The shape is always 2 numbers. The first number represents the number of rows it has. The second number is the number of columns. Okay, it's more than 2 numbers. Basically, each number represents the size in that dimension. So for example, this scalar here has a shape. It's basically empty. It doesn't have a shape really in that sense. If I wanted to check the shape of this, which we will do, is an empty tuple. This one has a shape of 2 rows and 1 column. We normally put the rows first when specifying the shape. So here the shape will be 2 comma, which means 2 rows. Of course, it doesn't have a column. This is a row vector. Sorry, it's a column vector. So it doesn't have any, we can see that it has maybe like a single column. This one, on the other hand, would be comma 3, because it's a row vector. It has 3 elements. But in all cases, right, a vector, we don't really worry about whether it's a row vector, a column vector. We just say a vector is a vector. Okay. Then a matrix. So this matrix will be represented, the shape will be 2, comma 2, because it has 2 rows and 2 columns. This one, on the other hand, will be 2, comma 3, because it has 2 rows and 3 columns, right? Then when you're talking about multidimensional, then this is where you start thinking about, okay, where do I start from? Maybe the face is considered as you still consider this first. Typically, you would consider it this way, down, and then um, the face, and then the depth. So height, width, and depth. Okay, height, width, and depth. So this is basically 3 by 3 by 3, 3 comma 3 comma 3. That will be the shape of this. So every tensor has to have a shape similar to a NumPy ND array. It also has to have a D type. A D type is a data type. So like we talked about, you need to specify the data type, whether it is a floating point or an integer data type. And even the floating point has what we call, you know, um, full precision, which is float 32. It has half precision, which is float 16. It has quarter precision, float 8. And it has double precision, which is float 64, and so on. So we have different types. And we have broadcasting, which we talked about a little bit. I'm not going to go. Where is the tensor resident currently? Where would the computation for this tensor happen? Will it be in the CPU or will it be in the GPU? Okay. Then requires grad is a property you can specify to say, okay, this tensor, you each time you want to evaluate this tensor, calculate both the forward and then calculate the gradients. So every function in a tensor, you need to calculate the gradient, or every tensor you have to calculate the gradient. If you specify requires grad as false, the gradient will not be calculated. So because tensors can live in the CPU or GPU, right, makes it easy for you to write code once and you can run that code anywhere. So you can basically just transfer a tensor to a device. This is how you transfer a tensor to a different device. Just use the to function, x.to. So if x is the original tensor, which is in the CPU, I can create a new tensor x by transferring that x to CUDA. CUDA is the keyword or the name that is used for GPU. Mainly because CUDA, like I said, CUDA is the programming language for NVIDIA GPUs. Now, that's not the only type of, for example, if you are using Apple Macs, Apple Silicon, they have what we call Metal, which is a programming language for programming the GPU of Apple Silicon, right? And they have what we call a Metal Performance Shaders Graph, MPS graph, which is a framework for you to do neural network training, or sorry, neural network programming using a graph, computational graph, just like with CUDA. But so if you wanted to, you wouldn't say X to CUDA, you say X to MPS. That's the name for if it is metal. So others have different names like that. But for now, we just focus on CUDA because in most of the Jupyter notebooks um, we will use GPUs that have NVIDIA drivers, NVIDIA GPUs basically. So the GPU acceleration tensors allow you to do massive speed up for matrix operations and for training neural networks, like I said, because you can easily move the tensor into CUDA. But when you move tensor to CUDA, you now can leverage on the massive parallel processing, parallel computational capabilities of the graphical processing units, the GPUs. And this is what really makes things really fast. So as a machine learning engineer, you will be hearing a lot about GPUs, and CUDA and all of that. So PyTorch tensors are NumPy-like, right? But they are GPU aware and AutoGrad enabled. So this is kind of the summary of a tensor. We are going to do a bit of tensor hands-on before I come back to do more theory on the other aspects, like defining models and so on. But let's take a look at how we can just to understand a little bit about tensors. I'm actually going to go to the PyTorch um, website, and if you go, you click on tensors, and you see a lot of they basically have really nice tutorials here. You can try out the code. But the interesting thing is that you can actually open it on Colab. So if you check here, you see run in Google Colab. So I'm just going to click on this. You can also download the Jupyter Notebook or view it on GitHub. But I prefer Colab. So I've opened the Tensor tutorial, right? And I don't want to do everything from scratch, but you can basically run this. So you can see, like we said, tensors are very specialized data structures. You use them, they're like arrays and matrices. We've talked about all of that. And you can go and check all of this out, right? Um, you basically can. So like the similarity between touch tensors and NumPy ND arrays are so close that you can easily transfer a NumPy ND array into a touch tensor and vice versa, right? So it's very easy. So you would even see in most cases when you are doing stuff, you would actually have to use both Torch and NumPy. So for you to import PyTorch, remember, take note, we are not importing PyTorch, we are importing Torch. Like I said, Torch was a library in C, but when it got moved to Python, we called it PyTorch, but we still call it's still called Torch, you know, internally when it is imported. So I'm going to run this, right? And I don't know if I will have a GPU here, but I'll show you what happens, when you run this on a GPU. But for now, I'm running it on a CPU. Okay. Um, there's limited access to GPU, so you have to save your GPU compute on Colab. So you import. Now there are multiple ways you can initialize a tensor. So one way is just use a regular array of arrays, a regular list of lists in Python. This is the same way you would initialize a NumPy ND array, the same way. So now if you look at this, right, this kind of represents a matrix like this. So if you look at this, it kind of represents this matrix that we had here, where we had 1, 2, 3, 4. This is actually what this is. Okay, this is this. So it's good to kind of map our, mental model or intuitions of it. So this is it, right? Uh yeah. Um so if you look at it, this is this model 1, 2, 3, 4. And this is how we first of all generate it. So you see that we have two um we have two sets of braces here. Typically, this is how I would write it so that it's easy for everyone to kind of understand and map it to what we are doing. This is really what it is. So you can see I have this outer brace that represents, you know, the entire matrix, right? Then I have the outer brackets, rather not braces. These are square brackets. So these outer brackets represent the entire matrix. And then this inner bracket is used to represent each row in the matrix. So it's basically a list of lists. So this first one will have the 1 and 2. And then, of course, there always has to be a comma. And then this other one has a 3 and 4. And then inside the 1 and 2, you see that you have commas as well. You can't just write, when you are using Python this way, you have to put in the commas. You can't just leave them like that. So this generates for me that. And it's easy to create a touch tensor from it. You just use touch.tensor and you put that data in there. You put that representation of the matrix. I can actually now print the X data to see what it looks like. You can see it comes back to you and it says it's a tensor. So this is the important thing. It is a tensor. And it gives you this whole tensor. the interesting thing is that this tensor, you can also look at the shape. So you can do x data dot shape. You can look at the shape, and the shape is a touch dot size object, right? That's how touch represents shape. Unlike in NumPy, the shape would have given you just a tuple, a Python tuple. But for touch, they give it a class. And there's a reason for that because you can do more stuff with this, right? So just having a straight tuple is not enough. Okay. And then you can see it has 2, 2, like I said. So the shape is basically saying that 2 rows, right? And then each row has 2 columns. So one other thing that you find with both NumPy and Torch is I cannot use a list, an uneven list of lists, right? Uneven list of lists. I cannot use an uneven list of lists to make a touch. It will give me error. So let's say I had this one. I had 3 in the okay, AI is even smart. So I had 3 in the rows, and I had this first row of length 2. And then I have the second row of length 3, right? This is an error condition, right? It's not going to allow you. It's going to tell you that your uneven expected sequence of uneven, basically, it's expected sequence of length 2 at dimension 1. In other words, yes, they should all be the same length. They should all be the same length, right? So this means that, and this basically obeys the principle that we have. The principle that we have is that you you can use multi-dimensional arrays, right? But they have to be uniform, think. So that's a good thing to note. Now, this is another way you can create a tensor. If you already had a NumPy array, right? Like in this case, we actually had a NumPy array, which I'm going to take this out separately, okay, so that we can see what happens. So you have a NumPy array, and I'm going to print the NumPy array. Yes, so in this case, take note, this says array, while with touch, it said tensor, okay? So you have an array, which is an ND array, multi-dimensional, n-dimensional NumPy array. If you check the shape again, like we did with touch, um, so for NP, the shape, okay, you have a shape, which is sorry, so this is size actually. Um, Oh, I'm sorry. It should be NP array. So NP array dot shape. Okay. So the shape for here just gives you a tuple, right? But the shape for a touch tensor gives you a touch size object. But the most important thing is that the actual value in there is the same, which means it is 2 rows and 2 columns. Okay. So you now have a NumPy array called NP array. We can create a touch tensor from it by using this from NumPy function. So you just say touch dot from NumPy and you pass in the NumPy array. That's how you create a touch tensor. So if you do this XNP, this is what you get. You're still going to get a touch tensor. And then you can create touch tensors from other touch tensors. And there are a lot of different functions that help with that. So for example, this first one, once, right? So once like means create a touch tensor that has this, that's like X data in every way, including the shape, but except the actual information or data content, you change it and replace it with ones. So what this will do is that it's going to create a touch tensor that has everything like this tensor, but the actual numbers in will be replaced by this. So that means the data type, for example, By the way, I didn't check the data type, but you can also check the data type by dot d type, like we said. Use d type to know. So it says it's in 64. Interestingly, NumPy has a similar function. So if you look at this NumPy array, which is np underscore array, the d type, you also get the same thing, right, in 64. So if I do once like, I basically create a tensor, but you can see that it's the same as this one in shape, but it's replaced with one. That's what once like does. You can also have zeros like, which does the same thing, except that it replaces it with zero. The interesting thing is that if you also check the type of this ones like, it will inherit its type from the type of the previous one that you copied it from. So basically ones like it's like copying a tensor and then replacing its content with ones. Rand like is the same thing as ones like, except that it replaces with random numbers instead of replacing with ones. So it's basically saying make a copy of this tensor and then put random numbers instead of the actual values that are there. So, but you can also do touch.rand in the same way. Touch.rand will generate a random number, but you have to specify the shape, right? When you're creating a um, you know, you have to specify a shape. And typically a shape is specified as a tuple. So like in this case, the shape is 2, 3, and that 2, 3 actually means something. So you see, but the main thing is that it's going to have 2 rows and each row will have 3 columns. That's the shape you specify. By the way, I don't need to put a comma at the end, right? It will still work. But one thing to note is that um, let me see how this looks like. So the shape is still touch size 2, 3. Now I want to see if I put a comma at the end, whether I will still have a 2, 3. It doesn't. So the comma doesn't really matter. But if you were doing a single thing like this, a single vector, this would fail. Um, Okay, well, it doesn't. Interestingly, it actually generates a tensor, a vector that has size 2. So, yeah, this is an improvement in touch. I've seen other situations where this fails, because it fails to read this as a tuple and thinks it is a single number that has parentheses around it. So that's good. So this is a random tensor. You can also do a ones tensor, basically a tensor that only contains ones in it and specify the shape. So let me just put this shape, up here, right? And so we have the shape. So what this will do is it will give us a tensor that has ones in it, just like the ones like, except that in this case, instead of obtaining the shape from another tensor, we specify what the shape should be. And of course, because we are just specifying what the shape will be, right? The data type, touch is going to infer that from the data you supply, or it will use a default data type. But if you use ones like, it would have copied the data type from wherever you are trying to copy it from. So the zeros does the same thing. So that's why if you look at this, you now see that the random tensor will have 2, 3. They all have the same shape because we're using the same shape for the 3 of them. But the first one will give you random numbers, right? The second one will give you only ones, all ones. And the third one will give you all zeros because we specified it. So we looked at the attributes of a tensor already. You can look at the shape, the type, and the device. D type, by the way, means data type, right? So if I run this, of course, the shape will be 3, 4 because we already specified the shape here, right? Touch.rand 3, 4. Then the type is float 32, float 32. Because we did not specify a data type, it took a default of float 32. And then the device is CPU because we did not move it into the GPU. So one thing to know is that these are the default values. If you don't specify a data type, it will take a 32-bit floating point. If you don't specify which device, it starts off by specifying that that tensor should be in the CPU. So the things you can do on Tensor, one of the things is the is accelerator, the touch accelerator is available, is a way to check if there is an accelerator. An accelerator is basically another technical term for GPU. It just means that if there is a GPU available on this current machine, then you can now move the tensor into that. So remember I said the to keyword is what you use, or the to function is what you use to move um, computation into a particular device. So here we are specifying the device, and to get the current accelerator, touch accelerator or current accelerator. And there could be so many, right? It could be GPU, it could be CUDA, it could be MPS. I talked about MPS already. MPS is the Metal Performance Shaders, which is used for Apple Silicon. And there are a bunch of other ones as well, MTIA and XPU, which we can talk about. So now the interesting thing is that if I run this code, it will not, because there's no accelerator. If I actually run this just to show you if there's an accelerator. I'm not really going to go into accelerators yet. You see that it is false. And then if you want to see the accelerator name, right? Um, yeah, you see the accelerator name. Um, the current accelerator is empty, so there's no accelerator right now. I'm going to switch to the GPU, right? T4 GPU, and rerun this command so that you see what happens when there is an accelerator. Um, so everything you can do with NumPy, NDRS as per indexing and slicing, you can also do in a touch tensor. So like in this case, we created a touch tensor. It has ones 4, 4. And then the first row is tensor 0. Okay. Then the first column is this. So this means all the rows, right? But column 0. Okay. This is standard Python indexing, which you are not very if it's not very clear to you, I would advise go check it out, right? It's part of Python language. This is a two-dimensional indexing, right? This is a single-dimensional indexing. Let me break it down. So just to help, right? So first of all, yeah, we first of all create a tensor, okay? And let me just print that tensor so you can see it. So it's a 4 by 4 tensor. I specify the shape and it's touch.ones. So it will all have values of ones. Now, the next thing is the first row is tensor 0. So tensor 0 is the first row. So you see what it gives you. It's going to give you okay, so there's a problem here. I don't want to do this. Mainly because okay, okay. Okay, so tensor 0 gives you these four numbers, right? Tensor 1, of course, you will not know the difference because it's the same thing, right? And so on. That's the first row. Now, how do we get the first column? So you have to do, for you to get the column, you have to do the multi-dimensional indexing, which is available in Python. So you specify, first of all, the row. I could have said I want row 0 and column 1, right? But this will give me a single value because this single value is on row 0 and column 1. Or I could say row 0 and column 0. That will also give me a single value. This actually makes more sense if we don't just do touch at once, right? Let me just jump into it a little bit. So instead of touch at once, I'll do touch dot I don't want to do link space. Let's say a range, right? A range is basically a um um let's say 16. So then we'll do reshape, and then we'll want the shape, which is 4.4. Now I've jumped a little bit more into it, but what I'm basically trying to do is the A range. What A range does is it generates a touch tensor whose values, just like the Python A range, it starts from the beginning. It starts from 0 and, you know, gives you a list whose length is this number here. And the numbers are incrementally increasing from 0 to 15. So this will give you a touch tensor of size 16. But that touch tensor is a single vector, as you can see, right? It's a single vector. If I just do a range, it always gives a single vector. But I want a 2 by 2 matrix. So that's what the reshape does. Reshape allows you to take any tensor and change its shape, basically. So if I reshape 4 by 4, I'm going to come out with a 4 by 4, 4 rows, 4 columns. I can also reshape 8 by 2, right? 8 by 2. Now, 8 by 2. So it's still going to give me 8 rows and 2 columns. Now, can I reshape it to 8 by 3? It will give me an error because I don't have enough elements. 8 by 3 is 24. That is 8 rows and 3 columns. That means I need 24 elements. So this will be an error. If I wanted to do an 8 by 3, I would have to add 24 elements here. So this is just kind of this thing. So you cannot reshape if the number of elements is not enough for the reshape, right? But somebody may ask, I'm just jumping into reshape now, which I shouldn't have, but somebody may ask, okay, what if I just want to reshape it to 4 column, but I didn't know the number of rows? Then the one that you don't know, you use a -1, but the one that you know, you use this. So it's still going to reshape to 1 by 4. I cannot reshape 1 by 3 though, because 3 is not divisible by 16. You cannot equally split a 16 element tensor into 3 rows. There will be one left over, and that is not allowed. So those are some of the things. When you go, I would advise go and look at some of these other data tensor manipulation functions. So, but anyway, why I was doing this was because I wanted it to be clear so that when I say tensor 1, you know that it is the 4, 5, 6, 7. So it's the second row, right? And when I say tensor 0, it is the first row. Now, tensor 0, 0 gives me 0, which is position 0, 0, right? Tensor 0, 1 gives me the first row, but the second column, which is this. And so on. Tensor 0. Now, if I do tensor 3, 1, that means the third row, sorry, the fourth row, and the first column, which is this, sorry, the second column. Remember this index, this is an index actually. So it starts from 0. So 13, so 3 is actually referring to the fourth row, and 1 is actually referring to the second column, which is 13. But I want the entire column, right? I don't just want a single cell. So I use this indexing thing, right? This means I want the entire row. And the way I usually, so it gives me the entire column 2. And you can see it's 1, 5, 9, 13. And it gives it to me as a vector. And there's no difference between whether this vector is a column vector or a row vector, even though I'm taking out a column from it, right? But it gives me back a vector. So this is one thing. There's no differentiation between a column or row vector in TensorFlow or any of this. It's just a vector. A vector is a vector. So this is an interesting thing. Now, this is actually a short form of saying I want to start from 0 and I want to go to 3. This is kind of what we call slicing, right? I want to take slice from 0 to 3. There are 4 slices here. So that means this, by the way, this first index, this is the first index, and you use it to index the rows. If I put a single number, like this case, I want a single row. And then a single number here, I want a single column. But if I put a range of numbers like 0 to 3, right? This 0 to 3, I am saying that I want the first 3 rows. So I want the first 3 rows, row 0, row 1, and row 2. Well, okay, 0 to 4 is actually the first 4 rows because it's 0 index. So I want the 4 rows, okay? But one thing is that in this indexing, this number is what we call exclusive. So we're actually starting from 0. We're stopping at 2, not at 3. It is not inclusive. So I start from 0, 1, 2. So what this means basically is that I want rows 0, 1, and 2. And then from those rows 0, 1, and 2, I want column 1. So that means I want row 0 and column 1. Column 1 is here. So that will be row 0 and row 1 and column 1, which is this one, 5. And then row 2 and column 1, which is 9. So this actually is going to give me the 159. So 159, which is this. If I was doing if I was marking it this way. Okay. So unfortunately, I do not have enough time to go into indexing, um, you know, array indexing in Python, but it's something that is quite interesting and everyone should check. If I wanted row 0 and then I wanted columns 0, 1, 2, I'll do the same thing, right? And this time around, it will give me the first row, but to only give me the first 3 columns of it. And basically, that's what this is all about. So this indexing is available in PyTorch as well as NumPy and even a standard list. This comes borrowed from standard um, Python list because that's how standard Python list behaves. So that is how you can understand this. And by the way, the minus sign also means that um, you count from the end. So -1 means I want to count from the end. I want to check the first column from the end, right? So the first column from the end, in this case, I want row 3, but column 1 from the end. That's because my tensor got changed. But yeah, this is 15. 15 is row 3 and column 1 from the end. And you could also say, I want to get the last column. So when you put a colon like this without specifying the beginning of the slice or the end of the slice, it just means you want the entire thing, right? So in this case, the entire row and the column at the end, that's -1. -2 is the column that is penultimate, the column before the column at the end. So that gives you 2, 6, 10, 4. So I've kind of digressed from talking about tensors to just talking about indexing. You can join tensors, right, by using torch.cat. Okay, you can join tensors, and you can see that the same tensor, I joined it to itself 3 times. But when you are doing cat, you need to specify which dimension that you are extending in which direction you're extending. If you don't specify the dimension, it takes 0 as the default dimension. So you can see in this case, I did not specify a dimension, so it is stacking it vertically. In other words, it is increasing the rows. That's dimension 0. It's increasing the rows. But if I want to increase the column, to expand it column-wise, I use dimension equals to 1. So what this means is that it will extend it in the column-wise direction. So this is something to take note. Also, just to be sure, if I put dimension equals to 0, you will now see that is the same thing as not specifying the dimension at all. It still stacks it vertically. Now, what if I put a new dimension that didn't exist before? It will extend it in that direction. Well, okay, it doesn't because I cannot concatenate in a dimension that doesn't exist. There's another thing that we can use for extending, so we can talk about that. I actually thought it would extend. I've not tried that before, but with NumPy, perhaps it would. I've not tried it with NumPy either. So unfortunately, I don't have the time, but it's, let me leave that as homework for you to go try out. Right. So other things you can do with Torch, you can do standard arithmetic operations. So like this is a matrix. This is basically a matrix multiplication when you use this ampersand. Ampersand is a matrix multiplication, which is like a dot product. Um, and it's the same thing as using a matmul function, right? So we have a tensor and you have that same tensor, you transpose it, right? And by the way, um, we can see what this looks like, right? Let's see what this looks like. If I do a tensor and you see, it does the dot product straightforward. This is basically the dot product of these two tens of 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 against itself, right? The reason why you have to transpose is because you know that you need to line up dimensions. So look at this. We know that in matrix multiplication, if the middle dimension doesn't match, right, the matrix dot product will not work. And what do I mean by the middle dimension? So let's assume that you have three. This one is uneven. So you have 1, 2, 3, 4, 5, and 6, right? This is 1. Then let me assign this to M1, matrix 1. Then you have a second matrix, M2. And this is still the same as matrix 1, maybe the same shape, right? Um, you really cannot, if you do a dot product of these two, you're going to get an error. M1 at M2, right? You get an error. And the reason why, oh, hold on. This is list. So I need to convert this to touch tensors first. So yeah, I forgot that bit. So yeah, touch tensors. Okay. Now, so it says you cannot multiply those matrices because I'm trying to multiply 3 by 2 matrix by 3 by 2 matrix, right? And remember, when you're doing matrix multiplication, the middle dimension must be the same length. And what do I mean by the middle dimension? So let me clarify the ones that will work, right? 3 by 2 and 2 by 3 will work, right? This will work. Why? Because the middle dimension is the same. What's the middle dimension? These two. 2 and 2, right? They will work. Another one that will work would be if I did 4 by 3, 4 by 3 and 3 by 2. Yes, this will also work. Again, why? Because the middle dimension is the same. That is this 4 by 3 and 3 by 2. But if you were to flip this and change the order and say 3 by 2 and 4 by 3, this will not work, right? Why? Because the middle dimensions are not the same. Here is 2 and 4. So in matrix multiplication, this is a basic rule in matrix multiplication that the middle dimension must work. Now, in this case, you have a 3 by 2 and a 3 by 2, right? 3 by 2 and a 3 by 2 will not work, but if you transpose one of them, it will work, okay? So 3 by 2 and 3 by 2 will not work. But if you transpose one of them, right? 3 by 2 and 3 by 2 transpose, which in PyTorch you use dot T, right? Dot T is used to transpose any matrix. It will basically switch a column into rows and the rows into columns. Okay, this will work. This will work because we have transposed the 3 by 2. If you transpose the 3 by 2, um, it now becomes, let me write it this way. So it will now become a 3 by 2 and 2 by 3, simply because we transpose this 3 by 2, right? Similarly, if we transpose the first one too, if you can look at it, you see that if you transpose the first one, it becomes 2 by 3. So 2 by 3 and 3 by 2 will work. So that's why this is transposed. But if it is a square matrix, of course, it will always work, whether you transpose or not. And in this very specific case, right, a 3 by 3 and a 3 by 3 will always work. A square matrix will always work because the rows and the columns are the same dimension. So this failed, right? But if I were to now transpose this by using dot T simply transposes a tensor. You now see that it will work and it will give me a 3 by 3 because remember when I transpose 3 by 2, this one, and I have a 3 by 2 and 2 by 3, and the middle dimensions are the same length, and they'll disappear. In a dot product, the middle dimension will disappear and you'll be left with a 3 by 3, which is, you can go do all the metric stuff. Metrics is, by the way, a very interesting thing to study. You can go check it out and try all of these things. These are simple rules. This has to do with dimensions, by the way, not the actual matrix multiplication. But of course, the actual matrix multiplication is what PyTorch, NumPy, and all the rest will do for you, right? So another word that we sometimes use is matmul. With NumPy, we use dot. So we could also do the same thing here. So we could do tensor matmul. tensor, right? Again, this will fail because the middle dimension is not the same. Oh, hold on. Something has changed here. Okay, I think I may have. Let's see. Let me be sure. So, oh, yeah, okay. Tensor is 4 by 4 this time. Um, okay, I did not actually. This is M1, M2. Okay, sorry. I wanted to do the M1, M2, not the tensor and tensor. So if I now do M1 dot matmul, M2, right? I will still get the same error because the shapes, again, the middle dimension is not the same. Okay, so they cannot multiply. So so you can still do dot T, which is to transpose that one, and that will give you a 3 by 3. You can also transpose this guy, you know, first, and then you now have a 2 by 2 because when you transpose, you now have a 2 by 2. Because when you transpose the first one, your actual calculation changes from a 3 by 3 to a 2 by 2 because a 3 by 2 transpose becomes a 2 by 3, and this is a 3 by 2. So this will become basically a 2 by 3, right? And a 3 by 2. And you can see with that, the middle dimensions are the same length, 3 and 3. And that those two middle dimensions will disappear and you'll be left with the outer dimensions, which is 2 and 2. This also maps to how neural networks work, the weights. That's why I took a bit of time to look at this when we are talking about the weights and multiplying the weight by the signal. So anyway, this is dot products. These two do the same thing, right? They both do dot product. I wanted to try out another function that we use for dot product, which is dots. I don't know if that exists in PyTorch, but yeah, I think it does. Um, it's just to kind of follow the same convention. So either one will still be the same thing. Whether you do a matmul, hang on, one dimensional tensors expected, but got two dimensional and two dimensional tensors. Okay, so dots doesn't work on, dots only works on one dimensional tensors. That means the definition is different from what I think. But I know that in NumPy, the dot product is used to do the same thing as a metric. So in NumPy use dot to do a dot product, but in Torch use matmul to do a dot product. Then yeah, so you will see a lot of matmuls. So this is matmul of two tensors. This is another matmul, right? We created a tensor that looks like Y1 and is random, right? And then we matmul it. We need to transpose and then output. So another interesting thing is that in Touch, if you want to send the output elsewhere, you can either assign it like this, or you can specify out equals Y3 um, as part of the function call. They both do the same thing. They are both going to assign the result from this computation into this Y3. Okay. Then if you want to do an element-wise product, so you see the difference between a dot product and an element-wise product. A dot product, the middle dimensions have to be the same, but an element-wise product, the two must be exactly the same. If they are different, it will fail. So let's look at that. It's good to understand the difference. So here it's basically the same thing, tensor times tensor and tensor dot mul tensor. It's the two of them do the same thing, which is what we call an element-wise product. They have to have the same shape exactly, or they have to have the same shape in every dimension but the last dimension. That second condition is a bit more complicated, so I'm not going to dwell on it yet, but they have to have the same shape. So if I were to take M1 and M2, remember M1 and M2, they don't have the same shape, right? One is, okay, they have the same shape, right? So they will work. So I can do M1 times M2. Now, this is basically 7 times 1, 7. That's element wise. You multiply each element separately. 8 times 2, 16. 3 times 9, 27. 4 times 10, 40, 5 times 11, 55, 6 times 12, 72. So they have to be the same shape. You cannot do element wise on shapes that are different. So this is now the difference. They tell you that they do not match the same shape, right? There's something called broadcasting, which I will not talk about, which allows you to do element wise when they don't have exactly the same shape, but at least one dimension or every dimension, but the last dimension have to have the same size and shape. So, but we'll move on. Yeah, so all of this mole, so the math mole is to do a dot product, while mole is to do element-wise product. You can either use a function call like this, or just use the operator. These two will do exactly the same thing, just like these two will do exactly the same thing. Okay. All right. Um, yeah, so I think this has to do with the value that is used here. This has to do with the value. It says rand like is not applied for y1, which is a long tensor. And that's because we multiply two tensors. But I don't know why that should be a problem. Okay, I don't know why that should be a problem, but I'll skip that. Then other things you can do, right? You can aggregate all the values. We can do a sum, we've done before with NumPy, right? So we take this tensor and we sum it. And just to be sure what tensor is, right? Tensor is this. If you add all of these numbers, it gives you 120. Well, I need to check that, but it does look like it because I know that 1, 2, 3, 4 is 10, right? And 5, 6, 7 is 18, right? And well, we can prove that. But yeah, this should be the total sum, which should be 120. And you can see the type is an integer. So we have what we call in-place operations. These are operations that you do and you change the tensor. All these previous operations we did, you will notice that the tensor itself was not changed. I had to assign the results to a value. But um, if you want to change the tensor itself, you use an in-place. And to do an in-place operation, you use underscore. There's any method that has an underscore basically is a method that um is in place. So it's going to change the tensor, right? You don't have to assign it. Yeah, there's a bridge with NumPy, like we said. This allows us to easily pull data from NumPy into tensors or export data from tensors into NumPy. So to export data in a touch tensor into NumPy, just use the .numpy, right? The .numpy, that will give you the tensor. So this is a tensor, right? While this is a NumPy ND array. And then you can just do the same thing, right? Then to do the reverse, to convert a NumPy array into a tensor, use from NumPy, which we have already seen before, touch that from NumPy. So you're now going to create a touch tensor that comes from a NumPy. So you can also see how that looks like. And you see this is a tensor, while this is a NumPy array. NumPy array normally will be written as an array. And that's it. So that's just a quick intro to tensor. Well, it wasn't that quick. It actually took much longer than I was planning. But yeah, this is something you should look at a bit more. Right. So having looked at that, I would have jumped into AutoGrad, but I'm not going to jump into AutoGrad because there's so much, right? We've just looked at tensors. I would like to look at layers, right? And then I'm going to skip AutoGrad and we can handle AutoGrad on Thursday. But we'll look at how to build models and then we'll talk about the entire training loop. So how do you build a neural network now that we know basic um, you know, um, of tensors? Tensors are the base. But like I said, you start with this class called nn.module class. You have to import it. You typically import it this way. So you say import torch.nn, torch.neural network as nn. That neural network module has a bunch of other classes. The first one being a base class for all neural networks or neural network layers. Basically, any neural network you want to do, you start with this NN dot module. But it's not enough, right, to just do NN dot module. You have to now define in the init, which is the initialization function to initialize your neural network. You have to specify the architecture of the neural network. So I'm going to break down this architecture, how you initialize it. We start with the basic element, which is a touch neural network layer, basically. We have to understand what a layer is. So typically this NN module will handle the parameters, but the parameters are handled in the layer. The layer represents the parameters. And then other things, device placement and so on. Then we're going to talk about the common layers. We have everything in touch is a layer like I said. So you have a linear layer, which is basically a fully connected layer. Then you have a ReLU, which is an activation function. In Touch, activation functions are entire layers on their own, right? Then you have other kinds of layers like this conv2D, which is a two-dimensional convolutional layer, which is what we use for convolutional neural networks, right? CNNs, which we'll talk about next week. And then we have the LSTM, which is a layer. Also, LSTM is a long short-term memory. It's basically a recurrent neural network. And the recurrent neural networks are neural networks that um, basically have a feedback. Okay, they have a feedback, and that feedback allows them to kind of keep track of history, previous things that they learned. Okay, we're going to look at some of those. So when we have defined that with the init, you specify the architecture. Basically, architecture is, we'll look at it, and then we now define a forward method. The forward method is it now defines how the forward propagation works. So we had already talked about forward propagation. So the forward implements the forward propagation. Now remember, with touch, the backward propagation is done for you, so you don't need to figure that out. Once you figure out your forward propagation, then the backward will handle the automatic backprop, right? So this forward propagation is automatically called whenever you call the model as a function. The forward method is automatically called. So you have to define the forward method. If you don't define the forward method, your touch-based neural network is not going to be able to do forward propagation, and therefore it can't do anything. So PyTorch, like I said, would automatically handle the parameter registration. The gradient tracking will track all the gradients of all your parameters, right? And gradients of all your layers and gradient of all your functions, and basically all gradients, and then we'll do the back propagation for you automatically. So what you need to do is just think about your neural network architecture, the structure, right? And the flow, which is a forward, how flows across. And then PyTorch will handle other things, the training mechanics. So let's do a bit of hands-on on that as well. So I'm going to, for this, I'm not going to use the PyTorch. I'm going to pull out my notebook, which I had kind of started. I didn't prepare it all the way to the end because I want everyone to be able to see it as I am building it, right? Or maybe I just start a new one. I had it right here, but I can't find it again. So give me a second. Uh, oh yeah, there it is. So I'm going to bring this into the screen. Right. So this is my PyTorch basics. So right now, the only thing I have here is just a simple layer of neurons, right? Before then, let's talk about a layer, right? And what is a layer? If we remember, I kind of tried to explain that. So let me back up a little bit previous slides. We talked about feed forward. We talked about forward propagation. We talked about um, all of this. But let's stop here. This is a layer. And we said a layer is made up of a lot of neurons that perform their computations in parallel. That's what a layer is. And we say there are three kinds of layers. So we have the input layer, we have hidden layers, and we have output layers. Okay. Now I'm going to do something with these three. Um, so this is like a basic thing. If I want to pull this, right, let me pull this and put this into the notebook. Okay. And I'm going to precede this so that we can understand. So I have this, okay. And yeah, so this is a layer and this is another layer, right? This is three layers. Or you can consider it, let's consider it as a single layer, right? This single layer here, and this single layer has three inputs, even though they are marked XXX here, right? Um, when I was doing the code for a single layer, I had to manually do a lot of stuff. But with PyTorch, it's very easy, right? So I'm going to pull my inputs here. Let me just do my imports first. Right. So it's really easy. You just start with a simple this simple net that we have here. That's what this is, right? So let's look at it. A simple layer, basically. With a linear layer, you can do anything because a linear layer is the basic unit to implement a layer in PyTorch. It represents a stack of neurons, right? A layer of neurons where you can specify any number, the number of neurons that make up that layer, okay, by specifying the output size. The output size is the number of neurons that make up that layer. Then you specify the number of inputs that goes into each neuron in that layer by specifying the input size. Or if you go to the PyTorch documentation, they call it input features and output features. So in this case now, I want to define a very simple neuron. It has a layer, is only a single neuron in this layer, right? And this single neuron has three inputs. So to define that, you would define it by specifying three inputs, three, and one output. The one output represents the single neuron itself. And that's how simple it is. And then for me to do a forward this thing, there is something called FC, which is basically means fully connected, implement fully connected. That is FC is the name that we have given to this layer. So we are saying create a single linear layer and assign it to this FC. Okay. Then when I want to do a forward pass, just call that linear layer that I created and pass the X values, which is the input. That's as simple as it is. It's as simple as that. So I could now run this. How I can now create this model is model can be anything. Simple nets. That's it. I have created it. I've created my network. I can now do forward propagation by forwarding a value. Now, to forward a value, I have to first of all create a touch tensor. So I can create a tensor. Let's just, yeah, random input. Okay. Um, yeah, so I should have also imported touch as well. So I use the input. Remember, we said touch deals with tensors. So I have to create an input. Okay. This input, so let's do this in single steps so it's easy to follow. I first of all create a model and then I create an input. This input contains the value that I want to pass in. Now, remember, we have three inputs, right? So that's why the input has to have a shape of 1 and 3. Remember, 1 means a single data, a single row of data. And that single row of data has 3 features. That is why the terminology of features is actually more helpful, because we are saying that we have features. If you think of it that we are visualizing a two-dimensional array of data that is coming into this neural network that I want to train, the rows represent each data point, if you remember, and the columns represent each feature. So in this case, I only want to train it on a single row, and I generate the random data. So this is the random data, okay? And this is it. That's the input. I now pass this input into the model, and that gives me the output. So I just pass the input into the model, and it gives me the output. Simple. This output you can see has only a single value. It's actually a matrix, a 1-by-1 matrix, right? Because you see these double brackets. If it was single bracket, it would have been a vector. And that's the output. This is essentially what this neuron gives me as a single output. And note, I did not train it. I've not trained it. I don't have any data I want to train it to represent. I'm just doing forward propagation. So it gives me an output. You may ask, okay, what's this output? This output is because when you created this linear layer, the parameters were automatically initialized using random values. Okay. And that's it. The parameters were, so this FC has parameters in it. Basically, the parameters that represent the weight of this single layer, the weights coming in, right? That's all. And the bias coming in as well. So with this, I have simply implemented a single layer that has a single neuron, that is a single output, and 3 inputs to each neuron. Simple. Now, but the beauty of this is I can then extend this and say, okay, I want to do a layer instead of just doing a single neuron, right? I want to do a layer that has multiple neurons on it. So like this one now, we have an input layer, we have a hidden layer, we have an output layer. Okay. So if I want to implement this using PyTorch, it is very simple. So I could also do this. So let me take these ones. It's the same thing. I have a single input layer, hidden layer, output layer. Okay. So now I can create another class. So I create another class um um two layer two layer network. Okay. And remember it has to take from the nn.module, right? It has to take from the nn.module. So that's it. A two-layer network. It has to take from this. Then you have to define the init, which is what will initialize it. And this initialization, you have to specify some of the parameters. So for example, here I can specify the input size, that is the number of layers, that the number of neurons that I want in the input, or the number of inputs I want, right? Then I want the number of um, neurons in the hidden layer, and then the number of neurons in the output layer. So yeah. So again, just like this, you have to call super.init. Super.init is needed to call the parent class and do all of the bunch of things. Now, let me paste the screenshot so that we can see how our stuff will look like. So you can see we have input layer. In this case, the input layer, I'm not going to pass this in as parameters yet. I'm just going to hard code it. So let's just still stay with a simple implementation, and then you can go reason about it. So the first thing is we want the input layer. So self.input layer. Note that the names that you give to this are just any variable name, just like any other variable name in Python, right? It can be anything. Here it was FC, right? But here, I just decided to call it input layer. And the input layer is still a basic NN dot linear layer. And this linear layer will now specify the number of input features. So if you look at this input layer has three three input features, right? It had three input features. So we'll say three. And this is assuming you have 1, 1 coming in, right? Let's just assume each of these has 1, 1. So I'm not going to do anything, special. It has three input features. It also has three neurons on it. Okay. Even though, to be honest, here it was not specified the number of input features in this input layer. The other way is that we could even totally disregard this input layer, right? And assume that we just have a hidden layer. But I normally like putting an input layer, even if I'm putting it as a pass-through. Okay. So it has three inputs and three outputs. Okay. Then I now also want a hidden layer. So in this case, the hidden layer has three inputs. It has four neurons. So that's four outputs and three inputs, right? So each neuron has three inputs. 1, 2, 3. So you would put it as three inputs and four outputs, right? That's a hidden layer. Now this output layer, you can see it has two neurons and four inputs. Each of the neurons has four inputs. It's also a fully connected layer. So the output layer will be 4 and 2. So the interesting thing is you see that the input, this has to match. This is that same principle of the when I was talking about the matrix dot product, when I say the middles must match, it's the same thing. This 3 fits into this 3, this 4 fits into this 4, and you have these 2 coming out. Okay, so that's it. But defining the architecture, the init always defines the architecture, but the init is not enough to do the forward propagation. You need the forward function. So the init does the architecture. Okay. Yeah, so let's say do the architecture. Now, there's something I forgot here, right? Because we are not just doing, remember, hidden layer, we said there has to be an activation function. The linear layer doesn't have any activation function. Whatever you pass in, that's what it passes out. So in order for us to add activation, we will have to introduce an activation, right? And the way to introduce an activation, there are multiple ways. You can create a separate layer with activation, or you can do activation as a computation. The benefit of using a separate layer as activation is that the gradient is also saved in that layer so that the backward can be faster. The forward and the backward can be faster. But if you decide to say, okay, like what you have here, if you see what we have here, we actually have a function call that will do ReLU on the input layer before it passes it out. And then this X that is passed out will now pass here. But let's do something better. The input layer goes straight to the hidden layer. There's no activation, so I'm not going to put anything there. But in between here, I am going to put a ReLU, right? So self dot hidden, let's call it hidden activation, will now be nn dot ReLU. So I now create a ReLU activation layer, okay? So we can do in place or we can leave it. So now, it now becomes easy for me to do something like this. X equals self dot, or I can just call it activation. Let me just call it activation. So I am now, so here's the thing. Let's do it one at a time. So when you're doing the forward propagation, the first thing is the signal X comes in at the input, right? It comes in at the input here. What do I do to that? I pass it through the layer. So that's to pass it through the layer, step 1. the first step one in the forward pass, right? So step one is pass the signal, in this case X, through the input layer with no activation. Okay. You could also choose to do activation. So that will now be X. We assign it back to X and say self.input layer. So you can see that's the first step. I take the X, I pass it through the input layer, and the result from this function call is the output from that input layer. I assign it back to X so that X now contains the output from the input layer. So the next step is pass the signal through the activation function, which is what this does. So this same X, right, which is the output from the input layer, I pass it through the activation function, which I had already declared that it is relu. And note that you can call it anything. Okay. And since I declared the activation function as a layer, I can just call it as if I'm calling a layer. Okay. So this X now contains the value of the signal after activation through a relu function. Then the next thing is step 3, which is pass the signal through the hidden layer, right? So again, same thing. We just do self dot hidden layer and pass in X. Now again, remember hidden layer also has an activation. Okay. So we can now say step 4, pass the signal again through the um, activation function again. So again, this is for the hidden layer. So we'll do X equals self dot act. So we are passing the signal again. After passing it through the hidden layer, this is now the activation function of the hidden layer. Okay. Oh, hold up. I made a mistake. So let me back up because we said through the input layer will not have any activation. So it was wrong to have done an activation here. So there should be no activation between the input layer and the hidden layer. So we just take the output from the hidden layer direct and we put it into the hidden layer. And then we take that and we pass it through the activation function. And then this activation function, we now take that and that's step 4 now, pass the signal through the output layer. Okay, and you still do the same thing, X equals self the output layer. You pass this result here into the output layer and it gives you an output through the output layer without any activation. Again, remember the linear layer does not do any activation. So you now pass the signal through the output activation. So this now depends. If I want to do linear regression, I will not even pass it through any activation. But let's say I want to do a logistic regression. I want to train it to classify stuff. I still need to have another activation, right? So I can call this output activation and I'll use a sigmoid, nn.sigmoid, right? So I can then use that here and X equals that. And I return. Remember, since you are doing forward propagation, you must always return the value of X. And this is all. For simply defining this, right, you can see 1, 2, 3. Input, no activation. Hidden, I use a relu activation. Output, I use a sigmoid activation. And this is it. The interesting thing is that with this, I can take this model and I can train it on an exclusive OR problem, which is quite interesting because it has a hidden layer. Remember we talked about linear separability and all of that. We'll do that some other time. maybe by Thursday when we're going to look a little bit more at the training aspect. Okay. Even though there's a lot to talk about optimizers and so on. And this is simply it, right? A two-layer network. Now, I could also do a three-layer network. And this time around, I'm not going to do the kind of long explanation, right? Um, and I'll let you figure out how easy, how the code is, right? So again, we'll start with the init. And in this case, I'm going to, yeah, let me take this three-layer network. Um, it has input layer, it has two hidden layers, and it has an output layer. So in this case, you might even find that I really don't need to even define an input layer because that input layer was just passing stuff through, right? So I could just directly do a hidden layer, right? And call it hidden one. And that will be NN linear, right? It's giving me some large numbers, but I'm not going to do large numbers. So I'm going to just do, let's assume I need to classify exclusive or problem. And I have multiple um, numbers. Okay. So if let's go with this, right? I have three inputs. So I have three inputs. I'm basically doing hidden one. Hidden one has 1, 2, 3, 4 outputs, right? So three inputs, four outputs corresponding to the four neurons. Then hidden two also has four outputs corresponding to four neurons and four inputs from the previous layer. So hidden two will be 4, 4, right? And hidden three has a single output layer that is coming in, and then four of the input layers for the four inputs. So you have 4, 1. And that's it, right? And then just to show you how easy it will be for me to do the forward pass. The forward pass, I don't need to do all of this stuff. Well, okay, so there's a relu thing here, which it basically imports this from function. This is another way of doing it where I could call the relu directly, but let's still just self dot relu one is nn dot relu, and then um, self relu 2 equals nn dot relu, and then self dot um, let's say sigmoid equals nn dot sigmoid. Okay, so with this, the forward pass, I can just chain everything, right? I can just chain in everything. I can just do self dot self dot relu of self dot hidden one of x. So this is the output from that. You can basically chain it anyhow you like. Self dot relu 2 self dot hidden 2 of the input, right? Here you had self dot relu 1, self dot hidden 1, self dot relu 2, um, self dot relu 2, self dot hidden 2, and then self dot sigmoid of self dot output. And that is the value in return. So this is simply how you build definitions. Is effectively you translate this graphical model. What I normally do is I directly map the visual models into code. But you could also do a mathematical model if a mathematical model is given to you and you write the code for it. And PyTorch makes it so simple. So you see how simple it is. We have done complex neural network, with this. So that's it. I'm going to end it at this point. When we come back next, we'll continue from here. Basically, how do we train this network, right? And we will talk about AutoGrad. So let me see if I can complete this, right? let's talk about AutoGrad. AutoGrad is basically PyTorch's automatic differentiation engine. It tracks the operations on each of the tensors and it builds a computation graph automatically. So when you are doing a backward pass, it will it each every tensor keeps track of its gradient, the calculation that was done on it. So the beauty of AutoGrad is that you don't need to do any manual calculations of gradient, right? So with that, you can do back propagation easily. You can easily do optimization, gradient descent, and all of that, right? And you can train the neural networks easily. So there's a function called backward, which you will call not on a layer by layer basis, but on the entire network. You don't need to define that. The touch nn.module actually defines a default implementation of backward, right? That default implementation is enough in most cases. I don't think you would ever have um I don't think you ever have a you know I don't think you ever have a situation where you will need to define your own, right? What it actually does is that um so the method for training is that typically you when you have done a forward pass, like I said, all the tensors that are involved. Remember, all your parameters are held in tensors. The weight, the bias, any other value, even the input, right, that is passed in. Even though you probably wouldn't need to do back propagation on inputs, right? You normally do back propagation on the weights and the biases, the parameters. So those ones will have gradient enabled. The gradient is stored in the tensor. So the autograd is when you call forward, the calculations are done. Each tensor holds their own gradient. Then during the training, you will use a backward method on the optimizer or the loss rather, the loss function. There's a loss part to look at that. The loss has a loss of backward function that basically is used to then calculate gradients of the specific loss, right? With respect to, all of the model parameters. The one that you have specified that requires grad is true. So it does it using a computation graph, and the graph is typically discarded after a backward pass. So um, this is how it supports the dynamic model structure we're talking about. So the AutoGrad automatically applies a chain rule behind the scenes and allows your model to do the magic that it does. So before we close, I'm going to do these two things, right? I'm going to first of all just um, show you a basic training loop that uses PyTorch. I'm not going to explain too much all of the components of the training loop. We'll deal with that more when we come back. But we'll just do that and then we'll see how we can implement this feed-forward neural network, right, using PyTorch to solve that exclusive OR problem. So let's see how quickly we can do that. So we have two models we have implemented. We have a 2-layer network and we have a 3-layer network, and they all do the same thing. Now, we need to generate the training loop, right? For any specific problem. So in this case now, let's take the exclusive OR problem that we had before, right? And remember, we were saying we need so there are two ways I can look at this. Let me start with let's use a basic exclusive or um decision boundary problem, right? I'm going to use the second one. I'm going to use the second one. So I have let me just let me just drop this here. Uh, we will consider the exclusive OR problem. So here, right, is a definition of the exclusive OR problem. I have to import matplotlib. Okay. So the exclusive OR data set is this. I'm not going to use NumPy. I'm just going to directly create torch tensors directly. So the torch tensor, we have four here. These are the four inputs, right? The X, these are the four inputs. So when sorry, these are the four different data points we want to train on. If X, and I'm going to use zeros and ones. Here I was using a than, which kind of required negative, positive, but let's use a sigmoid. So for sigmoid, the exclusive OR problem is basically a, if you have 0, 0, the outcome, the training value, of course, I also put this in tensors, right? So the Y is what we want to train the labels, right? And the X is this. So yeah. Now to plot, I do need to let me bring in NumPy, or maybe I should just use NumPy for ease of yeah, for ease of for ease of interoperability, right? Um between matplotlib and Torch, right? So NumPy is really good to use when you're transferring data from one tool to the other. So in this case now, I just want to plot it, right? So I have the values of X, and then we have subplots. Then basically unique classes. We set the limits. So this time I will use -1 to 2, -1, x1, x2, right? Linspace will be minus 1 to 2, right? So effectively, I'm doing an animation of um the decision boundary for um for the exclusive OR problem, right? So you have it here. You can play the animation here. You will see basically trying to figure out if I can draw, but yeah, well, it's just an animation. Now, the main thing is we have this, right? We will have to plot a decision boundary around this. But first, let's even kind of just rather than plotting a decision boundary, something else I try to do is plot y against y, plot y against itself, right? Plot dot line, right? And I'll plot y against itself. And then plot. So we have a line plot, right? This is the correct, this is from another, looking at it from another point of view, right? Where 0 should be 0 and 1 should be 1. Actually, this should be a scatter. So 0 should be 0 and 1 should be 1, right? And now we will create an instance of our neuron and plot with it. So this is, we are plotting scatter. Now I create a new instance of a two layer, uh, let's just call it a network, neural network. Yeah, nets or model. Let's just call it model. So it is an instance of the let's use a three-layer network. A three-layer network. A two-layer has two outputs, so it may not predict properly. So we use a three-layer network, and we can then predict values for it. And we can say y hat, okay, is model, right? So remember, I can only pass a touch tensor into this model. So since I already have x as a numpy, I use from numpy, right? I don't necessarily need to do this float. I'll remove this just to reduce complexity. So I create touch tensor from this numpy x, which is the values that we want to predict. Okay. So this is the x when x is 0 and one of the x is 0 and the other of the x is 0. I want the y to be 0, right? 0, 1, 1, 0. So that's a simple one. So I do that and I get my y hat, which will give me all the four values. Then I want to plot it. So this should plot, but that problem, um, yes. Um, so this is mainly because, oh yeah, okay. Yeah, I now see why the float is. Um, a float is needed to convert. So that's okay. Otherwise it will fail. Oh yeah. Let me rewrite this. Okay, let me rewrite this because the three-layer network doesn't match the dimension of the XOR problem. So let's do that quickly. So let me just call it an XOR network, right? The XOR network. So the XOR network, I'll still make it a three-layer network, but the number of inputs, it should be two, not three. That's the main difference because we have X1 and X2. Those are we only have X1 and X2, so there should be two inputs. That's the only mistake. So X1, X2, the rest is good enough. We are using a sigmoid because we are predicting probability and everything else is okay, right? So we'll use XOR network, XOR network, right? Um, let's see. So you can't call numpy and tensor that requires grad. Use tensor to detach. Okay. So yeah, that's because I'm trying to the y hat is still a touch tensor, so we need to detach it. So we can now say y hat numpy. So these are some of the things we really shouldn't have. Y hash really shouldn't have gradient, but I'm not going to go into that. Um, Y hash shouldn't have a gradient because it's an output, it's a signal, it's not a weight. But I'll leave that. What this detach means is when you get outputs, sometimes you cannot directly convert them to numpy using the numpy because the that tensor still has gradient in it, and touch doesn't like that. Ideally, if we had done proper training, the tensor would have been detached, so it wouldn't be a problem. Um, yeah, so I'm still plotting the old one. So let me do this. Okay. So this is just the network without any training. You can now see that this one, without any training, see where it is classifying it. It's classifying it somewhat in the middle, you know, of that line. This is the boundary, one decision boundary that is kind of here. It's diagonally across, right? That's a projection in this particular plane that I have here. But um, but you see that in this case, it's doing it somewhere in the middle, right? It's doing it somewhere in the middle. So it is wrong. Now let's train. Okay. So let's just do the training loop. XOR network. Training loop, uh, same thing, right? We start with the epochs. We say we want to do maybe 100,000 epochs. Learning rate, we can just say, okay, learning rate. You can call it alpha or LR, whatever, right? 0.01. I'm not going to overflog this. Then we can also keep the losses. Um, Normally I don't even worry too much about that, but um, then we start the training loop for epoch in range of epochs. Okay. We do forward propagation, right? We can just say y equals um oh yeah, we need to get the x. Okay, so we need to get the x. Um yeah, we need to get the y. Then we create the model, of course. Then we have to create an optimizer. So that's the other thing I did not mention. Part of the training loop is for you to figure out how to do the gradient descent and so on. You need to specify an optimizer. And Torch has a bunch of optimizers. We'll look at optimizers on Thursday. So in this case, we are picking SGD. SGD is stochastic gradient descent optimizer, and it basically uses stochastic gradient descent, which is a derivative of the gradient descent, which we'll talk about later. Then you also specify what kind of criterion you want to use. Criterion basically is which loss function. Criterion means, by the way, these are just variable names, but they are kind of standard things, right? Um, So a BCE loss means a binary cross entropy. That's what BCE is. So if you remember when we're doing logistic regression, we actually were using binary cross entropy. So let's use that because we are predicting probability, right? We're not doing a linear regression. If it was linear regression, we would have used NN, would have used a mean square error loss, right? We would have used, and also Touch has a bunch of that. We could have used MSE loss, which is mean square error, which is what we're using for regression problem. But for classification, especially the single class in the category or two class in a category, we use BCE loss. So how do we now pull all of this together, right? So the first thing is that you have to do the Y hat, which is the normal thing. The Y hat is just model, calling the model. Okay, so when you call the model, you pass in the X values. Okay. Then you calculate the loss, right? And then after you calculate the loss, then um you do the gradient descent, right? By specifying which using the optimizer basically to do that. So it's not it's pretty straightforward, right? Because we have specified the criterion, so we just use this criterion. Criterion gives us a function, right? Which we can then call and get the loss by passing in the predicted value, the y hat, right? And the y value, right? Um, I don't want to do this other more complex y view stuff, right? Because then you can append the losses if you want, right? You can do the losses that append, which we have been doing before, just to append this loss so you can figure it out. Then the next thing is this, the optimizer zero grad. Zero grad means basically means clear previous gradients calculated by the AutoGrad algorithm. That's basically, because if not, you can end up mixing these new gradients that you want to calculate with the old ones. So zero grad is, you tell the optimizer zero out whatever gradients have been calculated before. Then you now do loss of backward. So you can see that the backward pass is done on the loss function, right? Backward calculation of gradients. The backward pass is done on the loss function. So you do a backward calculation of the gradients. That's what loss backward does. Because the loss function, basically. So hold on. Yeah, okay, the criterion is a loss function. It generates a loss which is a class that is capable of calculating gradients, right? Or an object rather that's capable of calculating gradients. So the loss is not actually a value. The loss is an object, right? That knows which loss function that it is to use. It knows the gradient of that loss function, and it is also able to get the gradient of all of the elements in the entire backward pass. So it knows how to do that. Then after that, optimizer.step. So optimizer then modifies. So optimizer.step is where the parameters are updated, right? Using the specified optimizer. So remember, optimizer is what determines how the gradient is actually applied. So think of this optimizer as the part of our code where we used to say dm minus equals dm minus equals, or dm, let me write it in full, dm minus learning rate times gradient, right? So this is the part that does the update, while the backward calculation is the part that did the calculation of the gradients, essentially, right? Which typically what we used to do, we used to calculate gradient by saying gradient equals whatever. What were we using in that time? We used to say um x, times y spread minus y. But this is simplistic, right? Because the actual gradient is not just this, right? Like I say, you have to take this and you have to pass it through a gradient of um, you know, the activation function, right? Which is G prime. So there's a whole bunch of stuff there which backward does all of that, basically calculates all the gradients for you. Okay. And then optimizer the step takes the gradients that are calculated, right? And because all of this is encapsulated in a class, these things know how to get what they need to get. So it's able to do optimizer step will now take this gradient that is calculated here for each um tensor, for each parameter, and is able to do this step. And then after that, the rest of it is history. So with this, right, we have trained the network. You can see how simple it is. This loop itself has been simplified. Yes, this is the same thing we used to do, right? Y hat, model, criterion. We create a loss function here. Let me take this. Yeah, let me take this out to this section, because you really don't, this is the section where you do backward calculation. You get the criterion, do this, do that. And, you know, that's it. That's it. If I run this loop now, hopefully it runs. And I will now redo. Yeah, I think I see an error there, but we'll fix that shortly. Um, Using a target size. Oh, okay. So I think I have a problem. The Y's were different. So I need to reshape it. So right now the Y's are basically 0, 1, 1, 0. Um, let's do this because think I have I need to be sure that the values match. So I may have to run this again because I have changed these values. So let's just call it train, X train and Y train. Um, even though I've not done test train splitting yet. Um, dot shape. I want to compare the shapes. Okay. And I'm going to restart everything. So I know some things have changed. Okay. So link space is taking a bit of a while. Um, right. So yeah, so X train and Y train are the actual stuff. So I should be using X train and Y train here. Um, um, when we are when we are doing this, it should also be Y train. Okay, so now for touch, this is some of the things that will happen. You need to know that you cannot put a NumPy NDRA straight into touch for any of the touch models. And right, so let's see. So the size of the X is 4, 2, and the size of the Y is 4. Um, using a target size as different to the input size. And this is in the criterion. So I think I have a difference in, let's see what my Y hat looks like. So I'm just going to try to troubleshoot this with 10 epochs first, or just one epoch first. So again, this is typically like if you had this kind of difficulty, you can troubleshoot. We'll look at troubleshooting later on. We can look at troubleshooting later on. So Y hat is 1, 2. So you can see there's actually a difference, right, in the tensor. And you will have this kind of problem if you are using sklearn. I was actually coming with a mindset of sklearn because um, Torch behaves a bit different. If you look at the shape, let's compare the shape. The shapes are not the same. Um, and you find that a lot of problems you have will be because of shape or mismatching shapes. So if you look at this, the shape of Y hat is 4, 1, right? But the shape of Y train is 4. So I need to reshape the two to match. Otherwise, my criterion will not work. I think one way to do it is I should actually reshape this to be a 4-1, right? I think I should actually reshape this to be a 4-1. So let's reshape this to be a 4-1. Um, because that is kind of the output that will come. So with that, that problem is solved. We have an epoch of 0, a loss of 0.6, right? So I've solved that problem just by matching the ships. I can now take this out because it's going to load up my display. And I'm going to set back to 100. Let's start with just 1,000 epochs. And we'll see how the loss looks like after 1,000 epochs. Um, let's see. Okay, so this only prints after 1,000 epochs. Okay, let's say 10,000 epochs. So now because we're training neural networks, we definitely need to give it more time. So you see the loss is dropping. Once you see your loss dropping, it's very good news. Okay, it's super good news. I can even print the loss, rather plot. Um, yeah, I can just plot the losses just like that. Yeah, so interesting how the loss goes this way. Okay. So it started off a bit like this, and it goes down. This is because of sigmoid, and maybe it's stochastic gradient descent as well. So you can see it doesn't just drop this way. At this point, the loss looks like it has converged. So let's now see how it does. Well, it's not good enough. Still have, it's not category classifying very well. So I will run this for 100,000 epochs, and this is where we will end it. At this rate, 25,000, 28,000, 30,000, 32,000, 35,000, 38,000. So while this is running, um, I don't know if we have any questions. Why do we always have to define a class? So there is another way. Defining a class is one way. There's another way you can use a built-in class called nn.sequential. nn.sequential, now my loss has really dropped, so this is getting better. nn sequential allows you to basically just stack layers together. And when you stack layers together, you can do anything you want with it. That's what nn, so we can look at that later on. Yes, so we after 100,000, I think we have much better loss. There was a local minima here. There's something called local minima, which we'll talk about when we are going to optimization. And it got stuck in that local minima, but it jumped out and we have dropped to a global minima. So if we run this, well, it doesn't look like it's, oh, um, well, it's interesting. It doesn't look like it converged. It's still looks like, it still looks like it needs more training. So, but anyway, this is how you do a training loop. It is obvious that my hidden layers are not enough. We need more hidden layers because the exclusive OR problem is a really complex problem. So we'll complete this when we meet. I think we run out of time. Thank you very much. Are there any questions?